Hey there, deep divers. Buckle up, because we are diving deep, deep, deep into quantum entanglement today.
We're talking those particles linked so tightly that if you, knew something about one, it instantly tells you about the other, even if they're, light years apart.
Whoa, okay. It's like they have their own little secret messaging system, defying all the physics rules we know.
It really is something else.
And the best part is, it's not just theoretical anymore, right? Like, this entanglement thing is already changing the tech world,
Yeah.
especially for security.
Absolutely.
Okay, yeah, you've got my attention. Before we go too far, though, let's rewind a bit. When did scientists first realize how strange entanglement really was?
Well, it might surprise you that even Einstein himself was really troubled by this whole thing.
No way, even Einstein. The Einstein.
Yeah, back in 1935, he co-wrote this paper with Podolsky and Rosen, and it basically threw a wrench into quantum mechanics.
So even Einstein was stumped by this. Okay, now I know it's got to be seriously weird. What was it about entanglement that threw these physics giants for a loop?
Well, they called it, get this, spooky action at a distance.
Okay, spooky action. I kind of like it.
Right. So entanglement, it seemed to violate this core idea in physics, this idea of locality, which basically says things can only directly mess with their immediate surroundings. No, like instant communication across the galaxy allowed.
So you're saying if you poke one particle, its entangled buddy across the universe shouldn't, instantly react.
Exactly. They thought there had to be some hidden variables, some missing pieces of the puzzle, to explain this seemingly impossible connection.
So they were basically like, quantum mechanics, we're on to you, you're hiding something.
Pretty much.
And this is but they were wrong. Decades later, and we now know not only is entanglement very real, but we're using it. It's not just some theoretical head-scratcher anymore.
Exactly.
So from baffling Einstein to actually having real-world applications.
This is a wild ride already. We're not just talking about slightly faster internet speeds here, are we? This is bigger.
Oh, way bigger. Imagine a world with communication so secure that it makes even the most skilled hackers cry. Wait, unhackable messages? Okay, now you're talking my language. But how does entanglement actually make that possible? Break it down for me. I need the Quantum Security 101 version here.
All right, so let's say you want to send a super secret message to a friend. With something called QKD, which is short for quantum key distribution, you both get a stream of these entangled particles. Think of them like tiny, perfectly synchronized locks.
Tiny locks with a quantum connection.
Right, and you each randomly choose how to measure your particles. Think of it like randomly turning a key left or right.
Okay, got it. I'm turning my tiny key.
And because your particles are entangled, your measurement results will match up in a way that only you two know.
So it's like by just measuring these entangled particles, you're creating a secret code, just like that.
Exactly. Now, if some sneaky eavesdropper tries to listen in on your quantum conversation, they mess with the entangled state just by observing.
They can't resist peeking at the secret message.
Right. And here's the best part. You and your friend would know instantly if someone was trying to eavesdrop. It's like a built-in alarm system.
So any attempt to snoop, and the jig is up. No way to hide.
You got it. And the best part, this isn't some sci-fi fantasy. This is real. Banks and even governments are already testing out early versions of these QKD systems to protect their data. The future is now.
Wow, okay. So we've gone from Einstein being totally perplexed to real-world security applications in just a few minutes. This deep dive is already blowing my mind, but we're just getting started, right? There's more to entanglement than just super secure messages.
Oh yeah, way more. What if I told you we could use entanglement to teleport information? And I'm not talking about beaming people up like Star Trek, not yet anyway.
Hold on, teleport information, as in the actual data itself, not just sending it through a wire really fast. I need more details. This is wild.
Okay, imagine you want to send your friend a really, really complex recipe, hundreds of ingredients, super specific temperatures, the works. With quantum teleportation, you wouldn't send the recipe itself. Instead, you'd use entanglement to send the information your friend needs to recreate that recipe perfectly on their end.
Okay, so I'm with you so far.
Uh-huh.
But how do we actually do that using these spooky particles? This is where I need my quantum teleportation for dummies guide.
Okay, imagine you have your trusty entangled pair, one particle with you, one with your friend. You perform a special measurement on both your particle and on the information you want to send the recipe. This links them in a way, but without destroying your original recipe.
So it's like you're taking a snapshot of the recipe's essence without ruining the actual cookbook.
Perfect analogy. You then send the results of your measurement, just 2 little bits of information, to your friend using a regular communication channel. These bits are like instructions for your friend, telling them exactly how to manipulate their entangled particle to recreate that recipe perfectly on their end.
So by sending just two little bits, you've essentially teleported that whole complex recipe. Talk about some serious data compression.
Exactly. It's like sending a blueprint instead of the whole building, really efficient. But there is one crucial thing to remember. We're teleporting the information, the essence of the recipe, but not the actual physical particles. Those stay put.
Okay, so no teleporting actual cakes
Yeah.
yet. But that does get me thinking. If we can teleport information, why can't we just copy it a zillion times? Isn't that, like, way more efficient?
Well, that's where a really fundamental principle of quantum mechanics comes into play, the no cloning theorem.
No cloning theorem. Sounds intense. What's that all about?
So this theorem basically says you can't make a perfect copy of an unknown quantum state. It's like you can share a secret, but you can't make perfect copies of that secret to give to everyone.
So you're saying the universe has trust issues. It's like you can share this entanglement thing, but don't even think about mass producing it. This quantum world is playing by a whole different set of rules.
It really is, and these rules have some big implications. This no cloning theorem, it's not just some theoretical thing. It's one of the big reasons why quantum cryptography is so powerful. It means the information encoded in those entangled states is truly unique.
So it's like every entangled pair has its own unique fingerprint, impossible to forge. Next level security for sure. Okay, but let's zoom out for a sec. We've talked about using entanglement for those ultra-secure messages and even teleporting information, but can we scale this up? Like, could we build a whole internet on this?
Now you're thinking big. And you're not alone. Researchers around the world are working on building what they're calling the quantum internet.
A quantum internet? That's straight out of Star Trek. Sign me up. But let's be real for a minute. What are the roadblocks? What's standing between us and this sci-fi dream?
Well, one of the biggest challenges is that these entangled particles, specifically photons, they're super fragile. Sending them over long distances through optical fibers and such leads to a ton of signal loss.
So it's like trying to have a whisper conversation across a crowded room. The message just gets lost in the noise.
Pretty much. Researchers are working on these super clever devices called quantum repeaters. They'd be like relay stations, strategically placed along the network to boost the entangled signal so it doesn't degrade over those long distances.
Ah, so instead of one long, fragile connection, you have shorter, more stable links.
Hmm.
Kind of like building a bridge across a huge canyon, you use multiple supports to distribute the load.
Spot on. But remember, we can't just amplify a quantum signal the same way we do with those classical signals we're used to. We've got that pesky no cloning theorem to deal with.
Right, the universe's trust issues are back to haunt us.
Exactly. So these quantum repeaters, they have to be much more clever. They use a trick called entanglement swapping to extend the entangled connection without actually making a copy of the information.
Entanglement swapping. Okay, now we're in the really complicated part. This is next level quantum stuff.
It is. It really is. But even if we figure out these repeaters, there's another big challenge waiting for us. Errors.
Oh no, errors, like my laptop crashing right when I need it the most.
Kind of. In this quantum world, those little errors can quickly become big problems, corrupting the entangled state and all the information it's carrying.
So we need some kind of quantum spell check.
Yeah.
Something to keep those errors in check.
Exactly. Researchers are hard at work on something called quantum error correction, or QEC for short. It's all about spreading that quantum information across multiple physical qubits, creating backups, and a way to spot and even fix those errors before they cause too much trouble.
So this QEC is like a self-healing system for our quantum internet, always on the lookout for those glitches and bugs.
A great way to put it. It's really complex research, lots of super smart people working on it. But even with all these hurdles, the potential is huge.
Yeah.
Just imagine a world where we can use entanglement to create insanely powerful quantum computers, all linked up in a global network.
Okay, a global network of quantum computers, all connected with the power of entanglement. Wow, that's a lot to process.
A lot.
To process. In a good way, right?
Yeah.
Like, what could we actually do with that kind of power? What's the best case scenario here?
It's really hard to overstate, honestly. I mean, imagine being able to design materials, but like atom by atom, from scratch. Or really getting to grips with how biological systems work so we could design things like gene therapies, really targeted stuff.
Yeah, makes sense. I guess simulating something as complex as a living cell, that takes some serious computing power.
Oh, absolutely. We're talking about breakthroughs in medicine, material science, even AI. Imagine a world where we actually understand how the brain works or how to design the perfect drug.
Okay, you're painting quite the picture here. A future with custom designed materials and medical breakthroughs, that's huge. But let's be real, how long until we get there, realistically?
The million-dollar question. We've made a ton of progress, but those challenges we talked about, those are still big ones.
The repeaters, the signal loss, that whole quantum error correction thing?
Yep, all of that. It's like we're trying to build the most intricate machine imaginable, but the universe keeps bumping into the table, knocking things out of place.
Sounds delicate.
It is incredibly delicate, but that's what makes it so exciting. There are so many brilliant people working on this all over the world. It's truly a global effort.
And they're all working together to basically tame this wild quantum world.
In a way, yeah. It's about taking these bizarre quantum rules and instead of just being amazed by them, figuring out how to make them work for us.
So from Einstein's skepticism to unhackable messages and a peek into this future powered by entanglement, this deep dive has been quite the journey.
It has. You really start to appreciate just how weird and wonderful this quantum world is, don't you?
Absolutely. And the fact that we're not just like observing these quantum phenomena from afar, we're learning to actually control them. That's pretty amazing. So for our listeners out there, what's the one big takeaway you want them to leave with, the thing that'll really stick with them after the episode's over?
Okay, how about this? If entanglement really does let us make these instantaneous connections across vast distances, what does that mean for our understanding of space and time? Is it possible that this is the key to finally uniting quantum mechanics and general relativity?
Okay, so you're going for the big finish here. Leaving us with more questions than answers, I like it.
It's what this is all about, right?
Absolutely. Every answer just leads to more fascinating questions. Thanks for joining us as we took this deep dive into quantum entanglement. Keep those brains buzzing, and we'll see you next time.